So welcome everyone. I'm Mary Watson. I'm the Director of the Coastal Resilience and Sustainability Initiative, if some of you don't know me. And welcome to our second session of Lightning Talks. If you'll recall, the Lightning Talks are designed to help us get to know each other so we can form great collaborative teams and move forward with broadly interdisciplinary and impactful work. So I don't want to take up a lot of the time of our speakers today. We do have just we had a couple of last minute cancellations, so we do have a few extra minutes, and I'd like to both give the speakers a hair more liberty, but also perhaps have some questions at the end. So before I turn it over to our first speaker, I just wanted to acknowledge Amanda Mueller, who once again has pulled all of this off and will be running our session from, you can't see her if you're online. Well, yeah, I guess you can in her little pane online. But Jean-Paul, I welcome you forward, and we'll get started.
Thank you, Mary and Amanda. And Amanda, shall I start?
Yeah, you are good to go.
Mobile robots will transform coastal aquaculture. Since 2012, I have been building, designing, prototyping, and programming mobile robots for environmental monitoring applications. On the left-hand side of your screen, you see an aerial water sampling system that I started to work on as part of my PhD. Through failure, I learned valuable lessons about the intricate interplay of software and robots. Since 2012, the capabilities of sensors and computation and deep learning have unlocked promising capabilities for mobile robots, especially in challenging application domains like coastal aquaculture, shown on the right-hand side of your screen. In these application domains, all of the challenges of mobile robots are amplified and compounded by problems of intricate, delicate tasks like rethreading nets and also unmerciful salt. But the promise of mobile robots, that they might help amplify our understanding of the environment while letting us increase our production of carbon-negative proteins and perhaps contribute to economic vitality and clean the water. All of these together inspire me to try to tackle these kinds of domains. Our team is interdisciplinary and consists of faculty from biological and agricultural engineering and computer science. We seek to better understand how oyster harvests are impacted by waterborne bacteria. Our research is sponsored by the USDA and the National Robotics Initiative from NSF. To do this, we will build building collaborative human-robot systems, both with aerial and surface robots, that will carry sensor payloads so that we can measure hydraulic and limnic properties to inform Bayesian models that will then tell us where precisely to send our robots. Our team is in the field, thinking and doing, and learning how to leverage these mobile robots that might someday contribute to coastal resilience.
Thank you.
Next, we have Katherine Anarde.
That's really cool stuff, John Paul. I'm going to do more of a program overview. So first, I'm Katherine Anarde. I am an assistant professor in the Department of Civil Construction and Environmental Engineering. I started 2 months ago. I am a coastal engineer and geomorphologist, and I created the Coastal Hazards Lab here at NC State. And at the Coastal Hazards Lab, we're primarily interested in measuring coastal floods and their impacts to landscapes and communities. So we're interested in measuring floods at the beach during high surge and wave events. So the image on the left was taken on Monday, this past Monday, on Pea Island on the Outer Banks. It's kind of hard to see, but there's some poles across the beach, and those poles contain low-cost instrumentation for measuring waves and bed level changes during storms. So this effort is part of a much larger group of coastal scientists that are congregating on the Outer Banks this year to measure or to capture perishable observations of storm processes. And the reason we're doing this is to improve predictive models of landscape change. And that's really a central goal of my group here at NC State. So when I say predictive models of landscape change, I'm talking about both individual storms, so hurricanes, nor'easters, but also decadal scale models of barrier island evolution. And I've been working on a model for the past several years at UNC. It's called Cascade, and it is a framework for incorporating coastal management decisions into evolutionary frameworks. Okay, so we also measure floods during non-storm conditions, and this is sort of an entry into Natalie's talk. We are trying to measure sunny day floods. Sunny day floods go by a lot of names, also chronic floods, nuisance floods, high tide floods. I'm interested in measuring them in stormwater networks. So I've been working for the past year with a social scientist at UNC to create a sensor, a low-cost sensor that broadcasts in real time that can detect water levels in drains, and as the water levels percolate onto the street, identify in real time on a website this hazard to the community. I think I'm out of time. No? Okay, good. Okay, so the goal of this research is to identify the frequency, drivers, and societal impacts of sunny day floods. So the sensor shown in this photo is in Beaufort. We have one sensor right now, and we're installing several more across the state. But this one sensor, in the 4 months that it's been deployed, has identified 6 instances of road floods just due to high tides, but also 5 cases where the stormwater or the drain was at less than full capacity, and just a quick rainfall event overwhelmed the drains and flooded the roadway. That's it.
Okay, there you go. Thank you. Next, we have Natalie Nelson.
All right, hi everyone. My name is Natalie Nelson. I'm an assistant professor in the Biological and Agricultural Engineering Department. I've been here since August 2017. And today I'm going to mostly focus on a project, but I'm also going to give you a little bit of background information in terms of what my lab does. So first, to provide a little bit of background information, stormwater runoff is a dominant form of pollutant transport to coastal waters. So as we have rain that falls, the runoff that then accumulates can transport fecal matter, other pollutant sources, to coastal waters. And because of that, we tend to have shellfish harvest area closures and also beach closures immediately following storm events. And so coastal regulators are actually charged with then mitigating these different public health risks by implementing these closures. And our team is really interested in how we can develop better predictive models to help regulators, but also the public, anticipate when these different types of contamination events might occur. So we're really interested in how we can better implement what we call precision management in coastal waters, meaning not only developing models, but also having the data collection infrastructure with which we can then develop models to implement precision management approaches. So for example, we have one tool that we're currently developing and pilot testing called Shellcast, in which we provide a weather-based forecast that allows for shellfish growers to anticipate when these different types of storm-driven closures might occur. And although we are interested in the effects of storms, we're also trying to think about what other types of landscape flushing events can lead to different contamination events that could also be of concern, either from a shellfish harvest perspective or just from the public use perspective of swimming, using beaches. And so one that we're especially interested in is sunny day floods. So thank you, Catherine, for setting me up. So sunny day floods are starting to increase. We see them in many different areas along the coasts. Here I have a photo from a neighborhood where I have family that lives in St. Petersburg in Florida, and they're regularly experiencing these types of sunny day floods. And so I personally experienced this a few years ago when I was visiting. They had extensive sunny day flooding, and I realized that we spend a lot of time thinking about how storms can then cause contamination events, but it's really unclear to what extent these other types of floods might be similarly leading to contamination. And so what we're trying to now do, we just started a project, so we just received funding. We plan on going out and with sondes and also with grab sampling, collecting samples to then try to better characterize what exactly are the water quality consequences of this type of event. And so part of the reason why I also wanted to present on this today is because we're seeking collaborators. So I've already connected with Katherine, which is fantastic, but we're looking for sites that would be really suitable for this kind of work. So if you're out there and you know of a place that is routinely flooding and you think it might have water quality impacts, I'd love to hear from you. Thanks.
Perfect. Thank you. All right, so next we have Sarah Spiegler. Sarah, if you're ready.
Yep. Hey, everyone. My name is Sarah Spiegler, and I'm the Coastal Resilience Specialist at North Carolina Sea Grant. I'm out in our Morehead City office at the NC State Center for Marine Scientology, and I have worked on issues of climate change and coastal resilience for almost 10 years in North Carolina. And I started with Sea Grant as the coordinator of a program called the North Carolina Sentinel Site Cooperative, which focused on the impacts of sea level rise on coastal habitats and communities. So you can see in this photo the high water levels that I took of Beaufort and the North Carolina Rachel Carson Reserve in 2019, and this is during a king tide event. So today I'm going to give a brief summary of new resilience efforts in the state after Hurricane Florence made landfall in Wilmington on September 14th, 2018. And next, please. Okay, so we all know Hurricane Florence was a slow-moving storm, and the record rainfall caused extensive flooding, much of which was in inland counties and in low-income communities. According to a NOAA report, the total wind and water damage was approximately $24 billion, and damage losses in North Carolina were at about $22 billion. So at the end of October 2018, North Carolina Governor Roy Cooper issued Executive Order 80, which is North Carolina's commitment to address climate change and transition to a clean energy economy. You can see in this list that EO 80 includes goals like reducing greenhouse gas emissions to 40% below 2005 levels by 2025, integrating climate change mitigation and adaptation practices into all our cabinet agencies, and also developing a climate risk assessment and resilience plan. This plan was published in the summer of 2020, and it was the culmination of a lot of hard work by North Carolina agencies and stakeholder groups. And in addition, the North Carolina Office of Recovery and Resilience was also created, and it is in the North Carolina Department of Public Safety. And we are proud to say North Carolina Chief Resilience Officer Jess Whitehead was a North Carolina Sea Grant Extension Specialist before she left to lead the new NCORE office in 2019. Next, please. So the 2020 plan also calls on the state to establish a North Carolina Resilient Communities Program, and they called this one of 4 priority resilience initiatives. And it recognizes that improving local resilience requires access to expertise, technical support for analysis and planning, and also funding for long-term resilience. And so as part of this, the North Carolina Resilient Coastal Communities Program was funded in 2020 through a grant by the National Fish and Wildlife Foundation and also the North Carolina General Assembly. And the North Carolina Division of Coastal Management is leading this program with support from partners that include NCORE, Sea Grant, and the Nature Conservancy. And so you can see in this map, the pilot program includes 27 coastal communities that are working directly with contracting companies, and they are going to develop locally driven resilience strategies and projects. There's going to be in this program a focus on natural and nature-based infrastructure, and so it's going to help communities reduce the impacts of coastal hazards such as flooding and storms. And I think I'm almost at my time. Thank you.
Thank you. Thank you, Sarah. Next, we have Aranya Chakrabortty.
Oh, thank you, Amanda. Hi, my name is Aranya Chakrabortty. I'm a professor in electrical and computer engineering department here at NC State, and I work in electric power grids and their controls. Next slide, please. So today I'm actually going to briefly talk about microgrids, which are small power grids that can cater power to neighborhoods and small communities and small villages without depending much on the main power grid infrastructure. Microgrids consist of small power generating devices such as rooftop solar, small wind turbines, energy storage and batteries, diesel generators, and residential loads. And now these days we also have electric vehicles and charging stations. And as you can see in the picture, these devices communicate with a central operating station and also between each other continuously all the time, just to make sure that they're all working in sync with each other. Click, please. And they also take individual feedback control actions just to make sure that they can maintain safe values of the voltages and the 60 Hertz frequency. Otherwise, that will create huge problems for the loads. Click, please. However, currently the control laws of these devices and the communication laws are built completely agnostic of each other. So when disaster strikes like hurricanes, torrential rainfall, wildfires, all of these natural calamities, when they happen and create damage to the communication lines or the control equipment, then there's no way for the controllers and the communication networks to adapt to each other because their core designs were not consistent to begin with. So that is what we are working on, and what we intend to do is to design the control infrastructure and the communication infrastructures in a co-designed fashion so that they are consistent with each other from the very beginning, from the design phase. And that co-design and consistency will buy us more adaptability and resilience when natural disasters happen and these devices need to talk to each other in a more coherent way. Next slide, please. So that was just sort of like the brief technical description. And here I'm mentioning some of the research keywords that we use for our research. And if any of these ring a bell to you, then please feel free to email me and we can talk. So I'm just going to read very quickly the different items that I have. So some of the tools that we use for these co-designs are combinatorial optimization, data-driven optimization, optimal control, wireless communication is supremely important for us, graph theory, system identification, weather forecasting, and smart charging of electric vehicles. All of these play a key role in everything that I talked about in the co-design process for microgrids. I'll just end there. And if you want to hear more, then I'm mentioning my email address over there. So please feel free to email me. Thank you.
Thank you. Next, we have Jeremiah Johnson.
Hi there, good afternoon, everybody. My name is Jeremiah Johnson. I'm an associate professor in civil construction and environmental engineering. And I'll talk briefly today about my research projects that aim to help achieve decarbonization and maintain or improve reliability in future power grids. Next slide, please. So a common mantra across my projects are, it helps to be flexible. Next, please. A key element when we think about power systems is that generation and demand must be balanced in real time. So this plot here shows the California Independent System Operator, the California grid, on a spring day, March a couple of years ago. And we can see throughout the day, they consume a bit more electricity in the morning and in the evening, and you have to maintain that supply-demand balance in real time. Next. As we decarbonize our grid, as California is doing and is well underway, wind and solar are particularly attractive renewables. They become very cost effective, but we are at the mercy of when the sun shines and when the wind blows. And so if we take those resources first, you'll see everything below the colored area here needs to be met by flexible generation. We need dispatchable, fast ramping resources to balance the rest of this demand. And deep decarbonization of power systems will require a solution in this regard. It will require off-peak generation that is clean, or demand response, or energy storage, or some combination of all three of these things. Next slide, please. So I'm going to briefly introduce 4 projects that aim to help solve this problem. The first question, can we use geologically stored CO2 in sedimentary basins to generate flexible geothermal power? Spoiler alert, the answer is yes to all of these things. So these are projects we're working on. This is with funding from the Sloan Foundation. And what we're looking at is coupling geologic CO2 storage with geothermal generation. So using CO2 as a working fluid to extract geothermal heat. So you get this double benefit, both CO2 storage plus megawatt hours from a clean generation source. Next, please. The next question, can solar power and grid scale batteries help meet peak power demand? So this is a collaborative project with Professor Joe DeCarolis, who's talking in a little bit. And we looked at the ability of solar itself to provide some of this peaking capacity. We are at the mercy of when the sun shines, but fortunately, there is a correlation between solar generation and peak demand at times. And it's even better when you can couple solar power with large utility scale energy storage. And so we're looking at methods and using real data to understand how much power system reliability can be provided by these resources that we are using for decarbonization. Next, please.
Seconds.
Okay. The next question, can we operate our power plants differently to reduce adverse human health impacts? And again, the answer is yes. So with our existing power plant fleet, we can simply run certain power plants less during certain hours and achieve really big reductions in adverse human health impacts. And this is a project with Fernando Garcia Menendez and some economist collaborators with NSF funding. And last advance, please. The last question, can we use buildings' heating and cooling systems to provide flexible demand to the power system? So this DOE-funded project, we are adjusting thermostats just a little bit, imperceptible to the occupants, in a way that changes the building's power demand, ultimately in a way that allows us to balance that supply demand in real time and integrate our variable renewables. All right, thank you very much.
Perfect, thank you. Next, we have Mo-Yuen Chow.
Yes, it's my pleasure here to share my vision about the use of citizen utilities for coastal resilience and sustainability. Next, currently, utilities are the main producers of electricity in the United States. However, the next wave of growth in electricity generation will be citizen utilities driven by the increased distributed energy resources penetrations. Some examples of distributed energy resources are rooftop solar panels, rooftop wind turbines, batteries in electric vehicles, etc., that will significantly change how people get and use energy. Citizen utilities will enable the general population to form their own nano and microgrids to provide sustainable energy locally and regionally. The growth in distributed energy resources and the rise of these citizen utilities has not been considered during community planning. This is particularly important in the rural and coastal communities of Eastern North Carolina because of climate change and increasingly unpredictable weather conditions and natural disasters such as hurricanes and flooding. Creating citizen utilities can provide a stable base for economic development, disaster recovery, and population growth in the region. Next. Our lab has developed the technology termed collaborative, resilient, and intelligent resource management for a sustainable human nature ecosystem, or in short, CRIMSON. That could be a starting point to the creation of citizen utilities for coastal regions. CRIMSON is the first of its kind technology and tool based on control theory that has distributed agents collaborating to perform distributed energy resources optimization and allocations to build resilient and sustainable rural and coastal community. We would like to form a multidisciplinary team to explore the needs and requirements from key stakeholders in North Carolina coastal regions. The team will include engineers, economists, climate change and weather scientists, urban rural planners, human behavior and psychologists, statisticians, extension specialists, the local economic development councils, electric utilities, and other key stakeholders to explore the interactions among nature, people, essential service, and disaster recovery. Outcome will include economic and technology development models, demonstrations of new technologies, and analysis of the process of planning, management, and operation of a resilient rural and coastal region management systems during normal impending disaster and recovery operations. We anticipated our R&D effort will provide a model for replication throughout the United States coastal and quite possibly to other parts of the globe. Thank you.
Thank you very much. Next, we have Heather Brutz.
Hello, everyone. My name is Heather Brutz. I'm on the Clean Transportation team at the North Carolina Clean Energy Technology Center. And we are working on a project on alternative fuel infrastructure for storm resilience in the Carolinas. Next slide. So this is a DOE funded project. The lead group who in this project is E4 Carolinas, but we're also working together with several councils of governments, Duke Energy and Advanced Energy. And what we are doing, this is a planning project where we are working to create a plan for North Carolina and South Carolina to enhance the resiliency of alternative fuel infrastructure, especially with regards to storms. So we both are looking at the infrastructure needed to support electric vehicle drivers during evacuations, and also to support the ongoing operations of first responders who are using alternative fuel vehicles during natural disasters. And we also are looking at ways that redundancy can be built into the system so that different sorts of fuels can be substituted for each other to provide greater resiliency. Next slide, please. So we have done a lot of mapping of the current infrastructure and alternative fuel users, especially among the first responder fleets in both North Carolina and South Carolina, and have worked to identify potential disruptions to the fueling infrastructure. We also are building out a model that looks at wait times at public chargers for electric vehicle drivers during an evacuation. And using that model, you can go and change different assumptions regarding things such as the state of charge of the vehicle when it starts, how far the drivers are going to be going, in order to basically see what the wait times would look like especially at DC fast charging stations along the route. The specific route that we are looking at is Wilmington going to I-95 along I-40. However, we do plan long-term to make the model public and in such a way that it could be easily adapted for other planners to use for other routes. We're also investigating best practices used elsewhere in the United States and the world to address some of these issues. And at the end, we will be formulating recommendations for public agencies to aid them in increasing the robustness of fueling infrastructure in the Carolinas. And so that is our project.
Thank you very much. Next, we have Joe DeCarolis.
Thanks, Amanda. So yeah, my name's Joe DeCarolis. I'm a professor in civil construction and environmental engineering, and I'll talk a little bit about some of my work on open source energy system modeling. Next. So I've spent roughly the last decade building an open source energy system optimization model called TMOA, which stands for Tools for Energy Model Optimization and Analysis. And the way these models work is they conceive of the energy system. It looks like the labels are messed up, but that's okay. So if you look at the diagram there, the model conceives of the energy system as a network where each of the green boxes is meant to represent a different energy technology, and those technologies are linked together in a network by the flow of energy commodities. And it's an optimization model. So what it's doing is minimizing the present cost of energy supply over the model time horizon. And it's trying to do that while making sure that there's enough energy supply to meet demand. There's a variety of other constraints that ensure that the system performs correctly. And it's also performing capacity expansion across a time horizon. So it typically starts with a characterization of the current energy system, and then we're looking at how the system evolves over time, over the next several decades under different policy constraints. The model's data intensive, so it requires specifying cost and performance characteristics for energy technologies across the whole energy system. And then out of the model as outputs, we get things like system-wide cost of energy supply, estimates of energy prices, emissions, installed technology capacity, and then these energy flows between different technologies. And there are a lot of other models out there that do similar work, but there's two key innovations in our work. One is that everything we do is open source. So all of the source code and data is publicly available, which means you can grab it and verify our published results. You can also build on our work by using our stuff as a starting point. And the second thing is that we need to do a better job characterizing uncertainty. And so our team has built a toolbox of methods that we can use to assess future uncertainty. And we're now using this to address big national policy questions related to future energy system development. So we have funding from the Sloan Foundation to develop an open energy outlook where we're focused on technology and policy pathways in the United States to achieve deep decarbonization. Next slide. And the other thing that I wanted to mention is that for several years, I've also been involved in the North Carolina Ocean Energy Program, Renewable Energy Program. And so this is just a sample of some of the
30
data
seconds.
Okay. This is just an example of some of the data that we work with. So you've got wind on the left, wave in the middle, and then ocean current energy on the right side. The top row is showing you capacity factor, which is an estimate of a metric of resource quality. And then in the bottom, that's been translated into the levelized cost of energy. So we've done a lot of work trying to characterize the technical and economic performance of offshore energy in North Carolina. And with that, I'll stop. And I'll also mention that I'm about to go on leave at the end of this year. So if this is of interest, get in touch in the next month or two. Thank you.
Thank you. Next, we have Veena Valam.
Thank you, Amanda. Hi, everyone. My name is Veena. I'm a PhD student in Dr. Michael Dickey's group at NC State University. Today, I'm going to introduce you to our approach for oceanic energy harvesting. Ocean energy is one of the significant, untapped, and reliable energy sources, which is renewable and has the potential to meet the growing energy demand. The researchers have found several ways to harvest ocean energy from waves, marine currents, thermal and salinity gradients, etc. Among these, wave energy extraction presents significant advantages. Waves may be seasonal, but they're more continuous and predictable when compared to wind or sunlight. The continuity and predictability are very important when it comes to effectively integrating this technology into electric utility grids. Despite the great progress, the existing wave energy harvesting technology has several limitations. For example, they're bulky and difficult to install. They're prone to corrosion. Besides, they have limited degrees of freedom. That is, they need to be moved in one or two specific directions to be able to harvest energy. To address some of these issues, we've been developing a new approach to harvest ocean energy. Next, please. As shown here, we make devices by encasing liquid metal in a hydrogel. Hydrogel is a polymer network that contains water. When metal meets water, it attracts oppositely charged ions, as shown in this animation here. Next, please. So when subjected to a wave, that is, upon experiencing a deformation, these devices generate current. Next, please. So with one more. Yeah. Things I want to highlight about this technology is that it is renewable energy and it has no carbon emissions. It is inexpensive, takes about a few dollars to make one. They're easy to make, takes about 10 minutes to make a device, and they can be made into any shape or size of interest and can be easily integrated with the existing technology. The idea is to have them as onboard power sources for low power technology, which requires about milliwatts to watts of power. And they're friendly to marine life, no rotating blades or noise, unlike turbines. They're also not prone to corrosion. Not only they tolerate salt water, but the devices require it in order to function efficiently. Finally, they have a scaling physics that offers highest energy harvesting efficiency when compared to the existing technology. With that, I'd like to thank my funding sources, my advisor, Dr. Michael Dickey, and all the teammates who helped me with this work. If this interests you, please reach out to us. Thank you for your attention.
Thank you. Next, we have Jared Bowden.
Hi, thank you for having me today. My name is Jared Bowden, and I work in the Applied Ecology Department and also with the Southeast Climate Adaptation Science Center at NC State. And I want to talk to you about how do we quantify changing precipitation as our climate warms, especially when you think about design. Next, please. So when you're thinking about design in particular, one of the things that's very commonly used are these precipitation intensity duration frequency curves. And basically what they amount to is on the x-axis here on the left-hand side is the rainfall duration, and then the rainfall depth on the y-axis. And then for different return periods, you can basically look at the probability that what type of storm was this in terms like a 100-year storm. And so, for instance, here I have Hurricane Fran in 1996 that impacted Raleigh. Was about a 100-year storm in terms of the amount of precipitation it produced in about 48 to 72 hours. When you're thinking about the future of climate and climate change and thinking about storms, the simple thermodynamics supports that the precipitation intensity should increase just because the moisture capacity of the atmosphere increases as temperatures warm. And we've seen over the recent years, including Floyd, Matthew, and Florence, these have been pretty extreme event storms. In particular, what I'm showing you here is Florence. And if you look at this scale, and this scale is based on this atlas here on the left-hand side, it's like 1,000-year event for much of Eastern North Carolina. And so you can kind of get a sense of the types of problems that it caused, such as you see here, I-40 and I-95 were underwater for days. Next, please. So when you're thinking about future design and you want to think about what happens in the future, you have to really go to the climate models themselves. But unfortunately, the global climate models are unable to really tell you a whole lot of valuable information about precipitation extremes. And so you need methods to arrive at how these extremes will change. And basically this comes through the effort of downscaling. And so basically there's two popular approaches. One of them is called dynamical downscaling, another is called statistical downscaling. Dynamical is much more computationally expensive than statistical, but it's basically simulates the physics of the atmosphere as the atmosphere warms, while statistical methods rely on some stationarity assumption as to what will happen. So that intensity, duration, frequency curves that I talked about before, the big question is, well, how will they change? Currently, when we think about design, we think in very stationary type things, and we were not really forward looking. And so I'm working with NCDOT to think about how to be forward looking in terms of what we should, for instance, how should we design I-95 or stress test I-95 to future conditions? And so if you look at different
30 seconds.
Thank you. If you look at different realizations of the climate, On the left-hand side, the dynamical simulations have upwards of 100% increase in precipitation as the climate warms by the end of century. But there's a lot of uncertainty remaining about, well, what should that number actually be if you're really stress testing the system? And so you can actually see that on the right-hand side is a larger ensemble of statistical downscaling methods. And so you can see their range can be actually smaller to much larger, upwards of 100% is what you see. And the ensemble mean of even the statistical methods that are available can be very different. And so we're trying to really understand, well, how much should the design values, for instance, be scaled in the future? Thank you.
Thank you very much. Next, we have Marcelo Ardone.
All right. Wait, am I unmuted? Can you hear me?
Yes.
Okay, great. Thank you very much for the opportunity to talk a little bit about our research on wetland, forested coastal wetland resilience. Marcelo Ardone, I'm an associate professor in the Department of Forestry and Environmental Resources. Next. So I don't have to tell this audience that sea levels are rising. That's the top there is a graph from the latest IPCC showing sea level change back to 1900 and projections depending on which scenario you use. You can see that sea levels have been rising and they're going to continue to be rising. The bottom graph, all those spaghetti lines are hurricane paths from 2006 to 2018. And so we've been interested in how this combination of sea level rise and more frequent and higher magnitude storms are affecting coastal forested wetlands. We're also interested in how human land use is affected in these systems. Next. So about a decade ago, I started studying a restored wetland in the coast of North Carolina. And in order to look at the restored wetland, we went and found some quote unquote reference wetlands nearby. And over the decade that we've been studying the restored wetland, what we noticed is that our reference wetlands were dying. Next. And so these systems were turning into these so-called ghost forests where you have all these dead standing trees. In some cases, those wetlands are being replaced by marshes. So you can see the marsh vegetation coming in the picture on the left. But in other cases, they're being swallowed by the sounds. They're being swallowed by the water, which is the picture on the right there. And so we're interested in why this is happening, what are the driving mechanisms, and what are the consequences. Next. We're very interested in ecosystem services. Wetlands are very good at sequestering carbon. So we collected soil cores from forested wetlands and marshes and used lead and cesium dating to estimate carbon accumulation rates. So our data are the two columns on the right. What you can see is that the forests sequester slightly more carbon than the marshes. So that means that if a forest turns into a marsh, it might not be a big deal in terms of the amount of carbon sequestration because they're pretty similar. This is what we found in North Carolina. Others have found different things in other places. So in Georgia, which is the first two bars there, they found that marshes sequester a lot more carbon than forests. So in Georgia, it might mean something different if forests are turning into marshes than what it means here in North Carolina. Next. We've also been measuring greenhouse gas emissions from these standing dead trees. Are they functioning as straws and facilitating the release of greenhouse gases from the soils to the atmosphere, or are they functioning as cores, as corks, holding those gases in the soil? And so the snags, you can see here,
30 seconds.
the snags are releasing greenhouse gases, but they release less greenhouse gases than the soils. But if you don't account for those greenhouse gases, you could be underestimating the emissions from these systems. Next. And so we found this in North Carolina. We're very interested in how, how common are these ghost forests? What are the consequences? And I've been collaborating with Kevin Potter from the Forest Service and others to map out the dead carbon all along the Southeast. And you can see that there's some hotspots in North Carolina, Louisiana, and other places. Thank you.
Thank you very much. Next, we have Astrid Schnetzer.
Hi, everybody. Can you hear me okay?
Yes.
Excellent. All right, next slide, please. Thank you for having the opportunity to talk to you about some of the projects we have on harmful algal blooms in the Plankton Ecology Lab. Foremost, I want to point out this is the hard work of many undergraduates, graduates, and technicians that you see represented in the slide. And the other thing that I want to point out is that algae are a good thing. They're at the bottom of the food web. We need them. If there's no algae, there's no whales, no fish. But some of these, a couple of dozen of these algae actually are having negative effects. So the problem clearly is that there is a global increase in the frequency, the extent, and the magnitude of these harmful algal blooms. And I want to talk to you about two of these producing algae that we're studying in our lab over the last couple of years. One is freshwater algae, which are blue-green algae or prokaryotes, cyanobacteria, that can produce a variety of cyanotoxins. And the other one is a marine diatom that can produce domoic acid. These groups of toxins can have all sorts of long-term and short-term impacts. If really in high concentrations, they can kill pets, cows, people have died from them too. You can see that the groups up there indicate that there's different organs that are affected by these. And it also shows you that we're concerned about varying pathways of exposure. So what you see right here is the bloom forming, and if so long as the toxins are still contained in the cells, a cellular toxin, they can be consumed and passed on and bioaccumulated over the food web. And all of these little examples have been implicated with these events. If the toxin leaks from the cells, it makes it into the drinking water. That's a potential concern. And then also during recreational use, you might ingest some of these toxins. Another series of studies also shows now that for cyanobacteria, the aerosolization of these toxins is an issue, and our lungs are really good filters. So there's a variety of impacts they can have. And if you go to the next slide, this map shows you a variety of water bodies where we've done summer studies, year-long studies on cyanotoxins and cyanobacteria that was supported by, unfortunately, cut-off funding agencies below that have helped us do this research. I just want to bring out a couple of things that we found and focus on some of those points closer to the coast, from the Chow River, Albemarle Sound, all the way down to Messingburg Sound, where we're actually looking at how the downward transport or downstream transport of some of these freshwater toxins can merge with marine toxins in some of those areas. What we find in all of these environments is that we typically find multiple toxins, and we find them year round, which raises all these questions about potential chronic exposure risks, even to low-level toxins. While we always thank you. While we always thought that we don't have too much of a Lake Erie or Lake Okeechobee situation, we did find record levels in 2019, which was a very active bloom year in the Chow River, which was 2 orders of magnitude higher as the EPA regulations for recreational use suggest. We followed up, we found it in varying species of fish, blue crab, clams, and so forth. And now we have an exciting new project where we look at different oyster farms together with Dr. Ben Horan from CMAS. And we're looking at oysters as sentinels, and we do find both domoic acid, which causes amnesic shellfish poisoning and is a marine toxin, together with those freshwater toxin, merge in some of those sounds and make it into the food web. And if you have any more questions, I'd be happy to answer those. Thank you so much.
Thank you very much. Next, we have Angela Harris.
Hi, I'm Angela Harris. I'm an assistant professor in the Civil Construction Environmental Engineering Department, and I study the environmental transmission of infectious diseases, and in particular have been involved in characterizing and identifying risk factors for microbial water quality and soil contamination, with particular consideration of rainfall events after particularly extreme flooding events. I'm going to be presenting today on a study that I'm involved in collaboration with Natalie Nelson and Chris Osborne, and we have a PhD student, Julia Harrison, who's involved in this work, where we're trying to develop a proof of concept for real-time monitoring of water quality in nearshore waters. Next, please. So elevated fecal bacteria concentrations in nearshore waters threaten public health, with the main 2 areas of concern being the safety of recreational waters for human contact, and then also sanitation of wild and farm shellfish. These 2 industries significantly contribute to economies of coastal communities. And each year, beaches and shellfish harvesting areas are closed due to water quality concerns. And this is often related to hazardous events such as storms and sewage discharges. Areas are closed in response to bacterial concentrations. Fecal indicator bacteria of like E. coli and enterococci are typically used, exceeding standards that are put forth by the EPA or state regulators. And fecal indicator bacteria are measured in water samples that use tests that require 18 to 24 hours before the results are known. If you hit next, the animation will come up. Thank you. Yeah. But we also know that water quality varies over very short time scales, even hourly, within minutes, we can see variability in water quality. So next. Thanks. And there's also evidence that postings are for water quality exceedances are not always reflective of current water quality. If you do next, thanks. And with this, there have been some models that have even estimated that postings can be inaccurate 50% of the time. And some of this inaccuracy can represent concerns for public health, where it's currently estimated that over 90 billion illnesses occur annually in the US due to surface water exposure. And so our question, so if next, I think if it might be cut off. Our question is can we predict fecal indicator bacteria concentrations using real-time measurements collected from multi-parameter sondes that measure several different water quality parameters? Next. So the research aims for this work, which is funded by the RISF program at NC State, is to use a multi-parameter sonde to measure multiple water quality covariates, such as pH, conductivity, temperature, dissolved oxygen, FDOM, total algae, turbidity. And what's somewhat unique for this analysis and fairly exploratory is a tryptophan-like fluorescence. And at the same time, we're collecting samples to measure E. coli and enterococci, both at high temporal resolution and also in high spatial resolution at some sites. And then our goal is to develop predictive models using machine learning algorithms to actually predict when exceedances occur using these real-time measurements. And so we would train those models with the microbial measurements that we collected as well. So yes, please reach out if any of these topics are of interest or potential collaborations. So thank you.
Thank you. Next, we have Eric Edwards.
Great, thanks so much. And I've really enjoyed hearing about all these research projects. It's really kind of amazing the scope and breadth of what people are doing. So I'm Eric Edwards. I'm in the Department of Ag and Resource Economics. I'm also the Associate Director of our center, CENREP. And I'm going to talk about two different projects that I'm engaged in. The first is sort of the effect of climate change on on-site wastewater treatment systems in the coastal Carolinas. So you may not be aware, but North Carolina is one of the highest rates of on-site sewage disposal in the country. About half of the houses in North Carolina have septic systems rather than sewer treatment systems. You can see pictures in North Carolina and South Carolina of some of these septic systems being exposed on the beaches. So the house you're staying at on the beach is disposing of its sewage right next to where you're swimming. And this is going to become more of a problem as water tables rise, freshwater tables rise, groundwater, and as sea levels rise. So what we're doing on this project is we're looking at what the economics are of fixing this. So, where could cities invest money to sort of fix this? Is the best thing putting in new best practices on new houses? Is it retrofitting old systems? Is it inspections, things like that? So we're going to have an economic framework of sort of understanding low to high costs and how much savings those provide under potentially climate change scenario. This is a large grant led by Jane Harrison at Sea Grant, funded by NOAA. So there's our website. It's probably too quick for you to hit on it. You can search for it. Next slide. Okay, good. So the other thing that I do related to the coast, and maybe not exactly relevant, but I think it's becoming more relevant to as we work on it, it's the economic impact of fisheries. On the left, we have the wild caught commercial seafood industry. On the right, we have the shellfish mariculture industry. Just how much economic impact these industries have on North Carolina, paying particular attention to future environmental constraints, either regulatory or just simply the environmental systems, how they're changing and how that's going to affect the resilience and sustainability of coastal communities, which really in large part, especially in the northeast part of the state, rely on coastal fishing. So again, we have a website for this. If you're interested in any of this information, definitely reach out to me in the Ag and Resource Econ department. Thank you.
Thank you very much. Next, we have Julie Swan.
Thank you, Amanda. If the people who are here on chat, if you can put your department affiliation or field into the chat, I think that would be very helpful for understanding who the audience is today. You can go to the next slide, please. And hit next 3 times, maybe. I wanted to start with a little bit about industrial engineering because a lot of people don't know what it is. We look at various kinds of systems and design, improve, install those systems. Lots of people work on, say, healthcare or manufacturing. And what we're trying to do is make these systems more efficient. That means faster or cheaper, more effective, that is reaching the right needs or the right objective, and potentially more equitable. We are sometimes also referred to as the people engineering. So when I think about coastal resilience and sustainability, there are a number of different things where I think that there's some good intersections with ISC. So you have very complex systems, long time horizon, uncertainty, limited resources that are being allocated, multiple decision makers. And we work through those in a lot of our problems. Hit next, please. Some strengths of the ISE department at NC State. We have health as well as humanitarian, including disasters. We've got people working in human systems and looking at interactions with technology. We've got strengths in manufacturing, in supply chain and logistics, and in data analytics and optimization. As one example of how this all fits together to make it more concrete, one of the things that several of us are involved with is pandemics, and we've been doing disease modeling and prediction for many years, and we're looking at a system, say a system like North Carolina, with schools interacting in universities and people going to work and incorporating behaviors and data and really thinking about interventions and response across that overall system. If you can go to hit next, please. And so in this sustainability area, there are lots of different systems where I see ISE as being able to play a role, looking at the intersection of some of these with this sustainability. So sustainable manufacturing, sustainable agricultures, and supply chains. Next slide. Next. I'm interested not only in research topics, but also in educational innovations. Recently, I had some discussions with several about starting a problem-based learning approach for multidisciplinary teams to take problems that we generate with discussions with stakeholders. And some of these are short-term, some may be long-term, but that the team of graduate students or undergraduates come together to solve this problem. Next, please. I envisioned that we could do this both at NC State, but then also develop a template that could be expanded to other universities. I've done this in the past in a different area, and it can really accelerate the capabilities of the graduate students, the faculty, practitioners, and in this complex interdisciplinary space. Next. Examples of external partners, companies, utilities, nonprofits, government, and you can see some of the different disciplines that you could include in a class like that. Next, please. As I mentioned, I have done this in the past in the humanitarian area where we solicited projects in healthcare and disasters. We later founded a center, and for about 10 years, we ran this type of problem-based class for graduate students that turned into lots of collaborations. So that's what I wanted to plant a seed with you today and on potential collaborations across the areas of ISE. And I encourage you to reach out to me. Thank you.
Thank you very much. That concludes our in-person and virtual talks today. We did have a few presenters that unfortunately had other commitments at the last minute across the university. So I did want to just share their topics with you in case you want to reach out to them in partnership. George Elvin was going to discuss rewilding architecture. And building an ecosystem enhancement. We also had Elizabeth Nichols, who was going to discuss Florence floods, forests, and wastewater treatment. And last but not least, Barbara Dahl was going to look at evaluating the potential of natural infrastructure for flood mitigation. And we do encourage you, if you heard talks today that you were interested in collaborating with, please reach out to those folks. All of the talks today were recorded and will be posted on our website, as well as the slide carousels will be there as well, so you'll be able to find their email information. And if you do have any questions about the Coastal Resilience and Sustainability Initiative, you can reach out to Mary or myself as well.
5 minutes.
Not yet. Julie, I do appreciate you asking folks for their affiliation, and so several folks have been putting that, but no questions yet.
Okay. Well, while one of you might think of a burning question, I just wanted to give you a little heads up at what's coming next in our series. So we've had 2 great sessions, very impressive sharing of research interests and capabilities across the campus. We're going to change gears just a little in our next 2 sessions and have some interdisciplinary panel discussions. We have some all-star folks who've agreed to join us and talk about 2 topics that I know there's widespread interest in based on the survey responses and my interactions with folks over the last month. So our first interdisciplinary panel is coming up in 2 weeks on October 27th, and it'll be a discussion of community engagement and co-production of research. And the 4 individuals who I'm going to announce momentarily are all going to come in person. So as we shift to being perhaps just a little more comfortable getting out and about as COVID infection rates go down, I'd love to encourage folks to maybe venture here to the venue here in Tally for that session. But we have Casey Bush, who's assistant professor in Department of STEM Education in the College of Education. Jean Goodwin, who's the SAS Distinguished Professor in the Department of Communication in Chaz, and she's the leader of or co-leader of the Leadership in Public Science Cluster. Susan White, who's the Executive Director of North Carolina Sea Grant and the Water Resources Research Institute, and I should not forget also NC Space Grant. And then Leslie Boney, who is the Vice Provost for Outreach and Engagement and Director of the Institute for Emerging Issues. And I invited Leslie in particular because this panel spans folks from different academic disciplines who look very differently at community engagement and can speak to what does it really mean to co-produce research or a research agenda with community partners. And Leslie can speak to what are community partners looking for when they look to interact with NC State, and can give some examples of community partnerships that we have across the campus right now. So really excited about them. And then 2 weeks later, on November 10th, we have a panel discussion on coupled human and natural systems. And the thematic area of coupled human and natural systems is the one where the most people in our collection of 230 plus faculty have expressed some interest. And again, we've got an all-star crew with different backgrounds. We have Gavin Smith, professor in the Department of Landscape Architecture and Environmental Planning in the College of Design, who does planning and policy. We have Dave Eggleston, who's Distinguished Professor of Marine, Earth, and Atmospheric Sciences in the College of Sciences and Director of CMAST, who's an ecologist, and Casey Dietrich, Associate Professor in the Department of Civil Construction and Environmental Engineer, who is, amazingly enough, an engineer. So we will have those three great folks talking about how do they think about coupled human and natural systems, what are the keys to working together, how do we communicate with each other, how do we develop an integrated systems approach and really work on bringing together the policy, the economics, the cultural, the physical, and the natural science aspects, along with the built infrastructure and technology aspects of building resilient and sustainable human and natural systems. So I hope you mark your calendars and convince all your friends to come and join us. And I look forward to very lively conversations. Any burning question?
No burning questions, but well, the one is the panel discussions will be available in person as well as virtual.
They will. We will still have our,
as well.
Yes, we still will have our hybrid format, so you can log in and view them on Zoom and put questions in the chat. But it'd be awesome if you are able to come here as well to participate in those sessions. So we are almost at our time, so thank you again for tuning in, and look forward to keeping going. And there are lots of other things happening within the initiative, so please go to our website often, and you'll see the new things posted there, and look forward to continuing to get to know all of you. And thanks again to Amanda for pulling together all the logistics of this session and keeping us on time and going smoothly, and to our Wolf Bite partners who have done a great job. So thank you very much.